Hi there, and welcome to this video. Thank you for having a look. It's on calculus, in particular differentiation, finding derivatives of various functions. And the functions we'll be looking at today, there will be 5 examples: a trigonometric, logarithmic, and quotient, with a little bit of explanation in the way of trigonometry. So here are the examples that we'll be working on. There are 5 here: trigonometric, logarithmic, quotient. So the first one is minus cos inverse of x. The second one is cosec of x plus 3 sec of x. The third one is a product, x squared tan of x. The fourth one, h of x equals 2 natural log of x. And the last one, a quotient, x equals 1 plus 4y cubed over 3. And we will be differentiating these and rearranging them sufficiently, so that they match up with one of the answers on the right, as we see listed. So looking first of all at number 1, minus cosine, inverse cosine that is, of x. We'll start off by letting y be equal to minus cosine inverse of x. Now, just to make the right hand side positive, we'll have minus y equals cosine inverse of x. Now let's take the cosine of both sides, and you'll see very shortly when this is justified. Cosine of minus y is equal to cosine of cos inverse of x, which equals x. Under what conditions is that true? Well, let's have a little look at that. So when is it reasonable, or indeed correct, to say that cosine of cos inverse x is equal to x? Well, function of x equals cos x is not a one-to-one function. So it's as far from being a one-to-one function as is possible, because on the domain, on the infinite domain from minus infinity to infinity, we see this sinusoidal wave, which simply repeats itself. So it's not just a many-to-one function. Well, it fits into the category of many-to-one, but there's an infinite number of x values for any given y value. And the y values fall within the range of minus 1 to 1. So pick a y value, and you'll find, by using a horizontal line test, that there's an infinite number of x values that will give you that y value. So we need to restrict the domain in order to be able to find an inverse function, because only one-to-one functions have inverses, which are also functions. Looking at this slide, we see a small part of what is y is equal to cos x, but I've restricted the domain from 0 to pi. Why did I do that? Well, from the previous slide, we remember reading that fx equals cos x is not a one-to-one function. It's as far from being one-to-one as is possible, because for any given y value within the interval of minus 1 to 1, which is the range of cos x, there's an infinite number of x values that yield that. And we'll see that now as we reveal the rest of this function. Now, we're not looking at an infinite domain, but we can see on this domain beyond 0 to pi, if we draw a blue horizontal line, all of the places where that horizontal line crosses the curve, it crosses at y is equal to 1/2. But we can see that for y is equal to 1/2, there is a multitude of x values that yields that. So we can see from the far left, minus 19 pi on 3, minus 17 pi on 3, minus 15 pi on 3, minus 13 pi on 3, and so on. All of these red vertical lines indicate x values that yield the same y value, meaning that this function, unless we restrict the domain, is many to one, and that means we cannot have an inverse function for this. Therefore, we restrict the domain from 0 to pi. Having done this, we can now take y equals cos x restricted from 0 to pi, and we can create the inverse function. We do this by swapping the variables. So we now have x equals cos y. How to make y the subject? Take cos inverse of both sides. Cos inverse x equals y. Well, it equals y because we've restricted the domain. Now we get this function where the domain of this new function, cos inverse x, is the range of the original function, which was cos x. So the domain is from -1 to 1. And the range of this new function, cos inverse x, is the domain of the original function, which was from 0 to pi as we restricted it. And if we use the vertical line test, we can see as we sweep from left to right that the vertical line only cuts the function in one place at any given point, meaning it is a function. Okay, so returning to this, we got up to the point where we had cosine minus y equals x. So, next step, take derivative of both sides with respect to x. So what's the derivative of cosine? That's minus sine. So we have minus sine, bracket, minus y, bracket. Then we have to take the derivative of what's inside the bracket. Y is a function of x. So we need to take the derivative of minus y, which gives us minus dy on dx. And on the right-hand side, derivative of x is just 1. So now on the left, we have a product of two negatives, which gives us a positive. So dy on dx times sine of y equals 1. Well, we can move the sine of y to the right-hand side, so we have dy on dx is equal to 1 over sine y. 1 over sine negative y. Now, noticing an identity in trigonometry, sine squared theta plus cos squared theta is 1. So 1 is equal to sine squared theta plus cos squared theta. So sine squared theta is 1 minus cos squared theta. This leads us to the next step. So we can rewrite sine of minus y as the root of 1 minus cos squared minus y. Now, looking back above, we identified cos of minus y as x in one of the previous steps. So now the final step is to rewrite, and we have 1 over root 1 minus x squared. Example 2, cosec x plus 3 sec x. Well, looking at the graph of this, it's going all over the place. So obviously it's changing everywhere all the time. So let's have a look anyway at how we take the derivative of this sum of trigonometric functions. So first step is let y equal cosec x plus 3 sec x. Now recognize the fact that cosec is the reciprocal of sine. So for the next step we have cosec x is equal to 1 over sine x. And sec of x is equal to the reciprocal of cos of x. So that's 1 over cos of x. Now, as we go through this, look carefully, we have y is equal to 1 over sine of x plus 3 over cos of x. At this point, we recall the rule for the derivative of quotients. F over g dash is equal to f dash g minus f g dash over g squared. So applying this now in the next step, we get y is equal to, well, the derivative of 1 is 0, so that's 0 times sine, which is 0, minus 1 times the derivative of sine. So that's minus cos for the numerator over the denominator squared, which is sine squared of x. Now for the second element there in the sum, 3 over cos of x, taking the derivative of 3 we get 0. So that's 0 minus 3 times the derivative of cos, which is minus sine. So we end up with 3 sine over cos squared of x. So we get minus cos over sine squared x plus 3 sine x over cos squared of x, leading us to the next slide. Continuing on from where we got up to in the previous slide, y dash is equal to minus cosine x over sine squared x plus 3 times sine x over cos squared x. So the next step here is to separate each of those terms. We've got 2 terms in that summation there. We want to separate them out. So the first term will become minus cosine over sine multiplied by 1 over sine. And the second term will become 3 sine x over cosine x times 1 over cosine x. This manipulation is what we do so that we can present the answer in the form of one of the options that we saw earlier. So, carrying on from here, looking at the first term, minus cos over sine is simply minus cot, or cotangent of x. 1 over sine is cosec of x. Now looking on the other side of the plus sign, 3 times sine over cos is 3 tan of x, and 1 over cos is secant, or sec of x. So our final answer, if we just rearrange that, is y dash is equal to 3 sec x tan x minus cosec x cot x. Moving on to example 3, x squared tan x. So if we just have a look for a start at the graph of this, we can see it looks almost exactly like tan of x, but as x gets increases in magnitude, that is, as it gets bigger in the negative direction and in the positive direction, that force elongates the tan curve, so the tan curve appears to become a straight vertical line. So the only place where the tan curve appears to look reminiscent of what it actually is, tan of x, is in the middle of this. As we move out to the left, it becomes vertical. As we move out to the right, it becomes vertical. So we're expecting a function, a derivative, which will yield very large results negatively and positively as we increase very quickly, getting outwards from the origin. So let's have a look at this. Okay. So y is equal to x squared tan x. Recall the product rule. Bracket f times g, bracket, dash is equal to f dash g plus fg dash. So, applying that here, we get y is equal to d on dx of x squared times tan of x plus x squared times d on dx tan of x. So, starting again from the left, d on dx of x squared is 2x. 2x times tan of x. On the other side of the plus sign, we have x squared times d on dx of tan of x, which is x squared times sec squared of x, which gives us 2x times sine of x on cos of x, plus x squared times 1 on cos squared x. And we will continue on to the next slide. Continuing on from the previous slide, we got up to 2x times sine x on cos of x plus x squared times 1 on cos squared of x. The next step that we perform is to multiply the numerator and denominator of the left-hand expression in that summation by cos of x. So we multiply up and down by cos of x. So we end up with 2x times sine of x, cos of x, over cos squared of x, plus x squared times 1 over cos squared x. Now notice that we have two expressions which have the same denominator. Now we can combine them. So we end up in the next step with x times 2 sine of x cos of x plus x squared, all over cos squared x. It's at this point that we notice another identity has revealed itself, that sine of 2 alpha is equal to 2 times sine of alpha cos of alpha. So in this numerator we have 2 sine of alpha cos of alpha in the form of x being the variable. So we can rewrite that, and the final step is x times sine of 2x plus x squared over cos squared of x. Moving on to question 4, h of x equals 2 times natural log of x. The natural log of x is something which we're familiar with. Multiplying it by a constant here, greater than 1, simply serves to elongate that vertically. But otherwise it will be effectively natural log of x. So starting out from just above 0, for x values just above 0, we will have a very negative quantity, and as x slowly increases towards the right, the value of h of x will rise up, eventually crossing the x-axis, and that occurs when x is equal to 1. So log of 1 is 0, and as x gets greater and greater, natural log of x increases, but at a much slower rate. So the rate of change is decreasing as x gets greater. Yep. So what that means is that for the derived function, initially it will have very large values, and then very quickly those will get much smaller, and then it will peter out towards almost a constant as it approaches 0. But we'll see that after we've found the function, the derived function. So h dash x is equal to derivative of 2 times natural log of x. Now we have a product here, so that means the derivative of the constant 2 times log of x plus 2 times the derivative of log of x, which gives us 2 times 1 over x, because the derivative of natural log is 1 over x, so we get 2 over x. Now we're familiar with 1 over x. 2 over x is just multiplying that upwards, so that gives us the red bathtub-like curve that we can see, which perfectly describes the rate of change of the blue curve. And for the last example, we have x is equal to 1 plus 4y cubed over 3. This time, notice we have x is equal to some function of y. So, in this case, we've reversed our variables. So x is the dependent variable and y is the independent variable. So this time we'll be taking the derivative in the form of dx on dy. Now, before we get into that, notice again that we have a quotient, and recall our rule for the derivative of a quotient. F over g dash is equal to f dash g minus f g dash over g squared. So, as I said, we have dx on dy, which is equal to d on dy of that quantity on the right-hand side, 1 plus 4y cubed on 3, which is equal to d on dy of the numerator, 1 plus 4y cubed, times the denominator, times 3, minus the numerator, 1 plus 4y cubed, times d on dy of the denominator, 3, and all of that over the denominator squared, which is 3 squared. So when we work that out, we end up with 12y squared plus, 12y squared times 3 over 3 squared, which means we have a factor of 3 in the denominator dividing the 12. So we end up with 4y squared. So in conclusion, just to look back at our index card, we had 5 examples. 1, which was minus cos inverse of x. That linked up with d, 1 over root of 1 minus x squared. Number 2 was cosec x plus 3 sec x. That linked up with e, 3 sec x tan x minus cosec x cot x. Number 3, x squared tan x. That linked up with a, x squared plus x sine 2x over cos squared of x. Number 4, hx equals 2 natural log of x. That matched with b, 2 over x. The last one, number 5, x equals 1 plus 4y cubed over 3, had a derivative of c, which was 4y squared. As always, thank you for watching. I hope this has been useful. The whole purpose is to help people and make things clearly understandable. So if you if you enjoyed this, give it a like, and please feel free to subscribe, as I'll be producing more videos regularly. Thank you very much.